So welcome everyone to this week's lectures on climate data science, and it's my great honor that I introduce today's speaker, Professor Li Yu from UC Berkeley. She is currently the Chancellor Professor for the College of Computing, Data Science and Society, Berkeley's new initiative on data science. And I have known Bing for years, and I know Bing doesn't like when I say I follow her footsteps. Everyone should have their own journey, but Bing has been an inspiration for me throughout my career. One thing I learned a lot from Bing is the courage to learn new things and try new things, and the faith and belief in doing the right thing, even when sometimes the tide of the discipline may swing, back and forth. And then so I'm very happy that Bing is able to make time to tell us a little bit about her recent work on interpreting deep learning models.
Thank you. Thank you, Tian, for the kind introduction. And so how much time do I have?
45 minutes, and then we'll do 15-minute Q&A.
Okay. So this actually we've been on pursuit of interpretable machine learning for the last 5 to 8 years. So it's actually accumulation works over the years. And let me just start. If I can turn my slide. So we live in the age of generative AI, right? 2 years ago, I was on leave from Berkeley, 50%, Microsoft Deep Learning Group. That's when ChatGPT happened. But recently, OpenAI released something called GPT-01 that's supposed to do reasoning, and that's supposed. So at the same time, there have been reports saying that ChatGPT can be inaccurate, but it's a huge help according to my students for coding. And about a year ago, Hinton, who was called the Godfather AI, left Google and started warning the danger of AI. Fast forward a year later, California had safety bill actually was vetoed like 2 weeks ago by our governor, because there was a lot of opposition from Silicon Valley. So then a few days ago, Hinton with Hopfield, another pioneer in AI, got the physics Nobel Prize. And yesterday, 3 scientists, David Baker, Abese, and I think last one, Jumper, the last 2 from DeepMind, and the first was from University of Washington, got chemistry Nobel Prize for their work. One was for their work, really be able to tell the protein structure AlphaFold from DeepMind, and Baker was for discovering new protein structures. So you can see that all this, the crown jewels of science, owning AI. That's what I read about these awards. Very exciting. And if you open the hood of AI, data science is an important component. It's not everything because there's hardware, there are many other things, but it's really a core, one of the pillars of AI. And we have 3 components, I think, presented by this Leap Center very well. Computing, statistics, and climate science. And by the way, I have been on the actually advisory board of Leap, and very happy to come here also as a speaker. And for many of you, I think, I suppose to work on data science problems. It's not just the modeling step. It's not just about deep learning. It's about the whole data science lifecycle and the ecosystem. And in the middle of this data science lifecycle, we have human right in the middle. We make many, many, many calls. And this process view of data analysis, of course, is not new. It's just a new name, has appeared in our early works of statisticians like Box, Cox, and Snell, and Nelder. And the topic I will try to address today is I would call scientific machine learning. There are many definitions. And my definition is that it's really used AI machine learning for scientific research to extract. Now we have the stamp of Nobel Prize to say this is a valid way to do science. And we have discoveries, compute new theory and knowledge. And at the same time, also build scientific principles, right? A lot of people in astronomy have been try to build in the symmetry principle into deep learning. And there's iteration between the above two steps, it's back and forth. And the results, I think, should be held to a higher bar than just machine learning for industry. It should be held to the scientific standards, open source and reproducible software. It's definitely required here, even though now deep learning industry definitely doesn't look like open source. Meta actually it is, but at least some of it, but not for say OpenAI and Google. So for the rest of the talk, I will try to give a definition of interpretable machine learning because interpretability, everybody has different meanings, and there's also explainability. And now I'll move to this adaptive wavelet distillation started a couple of years ago, but continued into projects in climate science and turbulence. And I will summarize and with some departing messages. A key component of scientific machine learning and CFAI is actually trustworthy interpretation. Because next week, if you are interested, I'm also on the I'm a scientific advisor at the Simons Institute for the Theory of Computing at Berkeley, and we're holding a whole week-long workshop about alignment, trustworthy watermarking, and privacy issues in large language model. So check it out. Starts on Monday, and you can be present remotely. And there it's really about alignment. So alignment, trustworthiness, I think it's a component of alignment. And alignment is about human with human, and who are the human we're talking about. And it's not just one person, usually there are groups of people. I work a lot on medical AI, and there we have doctors, nurses, administration, patients, health policymakers, and taxpayer because Medicare. So diverse group of people. Actually, I'm giving a talk there on Wednesday at 2 p.m. there about medical AI and alignment. And not so much overlap. So if you're interested with this talk, I would talk about reverted data science more, but mostly a different talk. So these are the examples where trustworthy interpretation is needed, right? If you do a prediction, you want to know where the prediction can be trusted. And there's people talk about just interpret the model. And for me, I want to bring in the trustworthiness because if the model is a bad model, why do you care to interpret? Maybe for algorithm development, but not for consumption by users. I want to understand the genetic drivers, a particular phenotype, say heart disease. And I'll mention about the cosmology. You want to understand the beginning of the universe. And FDA really facing tremendous challenges to know how to certify an AI algorithm. So what's going on right now there is like a lot of hospitals can put in AI algorithm into their operation under the banner of quality improvement. But if the algorithm can be transported to another hospital, you need approval. So we had this paper, it's really well cited by this point with my former group members to try to really put our mind together, work on different problems like just generic machine learning, neuroscience, and genomics. And what do we mean by interpretable machine learning? So we put our minds together, and really credits go to James Murdoch doing his second startup in San Francisco and Chandon Singh at Microsoft Research. Definition methods application. So one thing I think now is very accepted, not at the time, is really introduce relevance. The interpretation is to a particular audience and to a particular problem you try to solve. It's not just this generic interpretation. So for scientific application into machine learning, this is definitely very important to emphasize. And then you need to have a good model to have predictive accuracy, and descriptive accuracy has to be in context. Descriptive accuracy to the climate scientist in the audience, probably different from me. I'm knowing some climate science, but very beginning. And the interpretation will be tailored towards the level of knowledge of the receiver. Usually people agree there's a trade-off, but not always the case. There's interpretability or simplicity. There's no universal measure, but usually people think decision trees are the most interpretable. The small ones, you have 1 million nodes, probably is not interpretable. Small ones relate to logistic regression. Why? It's more interpretable than logistic regression because you can emulate, you can simulate the process in the human understand way. Logistic regression, even you have 5 terms, looks like linear, but you cannot do multiplications very quickly. You cannot quickly simulate the decision, right? You usually have to, a few, maybe people can do multiplications, and then you have random forests based on trees, but gets a little complicated, and deep learning is another level. But where do the large language models fit? That's the question. We have a small paper I'll mention at the end about this framework we developed for virtual data science. Actually, that the name was nicely suggested by Tian, like now 5 years ago. So trust in interpretation machine learning, it's earned. You need relevance, so the scientists, the domain experts say that, yeah, you capture something we know. And simplicity bridges that communication gap. And also you have to look at the data science process. You can completely come up with something seem quite reasonable with doctors just by not doing well, just by overfitting. So you also need the process to be truthful over vertical, seeking truth, but also report truthfully to the process. And our framework called the vertical data science in the paper 2020 build this PCS framework, predictability, stability, computability, which is really bring together machine learning with best statistical traditions and building on Leo Breiman's work, two cultures and bring it to one culture. So we started on the path of interpretable machine learning completely on machine learning problem. At the time, Jamie was my student and did a summer intern with Liu from Google. And he was very much a machine learner. And he was doing sentiment analysis. And at the time, there were only marginal interpretation for different words, but not compositional interpretation. So that's why he developed this thing for using really intricate mathematical decompositions, looking at the structure, the forward passing of information, and we define some compositional importance for groups of words and phrases for LSTM, that's like time series. So we basically can say that, well, if you have this phrase, not very good, not is kind of neutral, so very slightly positive, good is positive, and you become very good, and then things flipped. So this is give you interpretation on why not very good became negative. And this organization, so hierarchical using the contextual decomposition score, is using hierarchical clustering, right? That's a later work with Chandon with Claire 2019. And when later, also this paper generalized it to convolutional networks. And recently we have a paper led by my student Alia Xu, which is about to put it on the archive, generalize this, actually it's a lot more work to transformers. So now we have a whole pipeline, we can do this contextual decomposition CD, and not just for the input compositional, but also different layers, and to go for mechanistic circuits. And I always wanted to do science. Maybe I should have been a science major. So I was encouraging Chandon and say like, yeah, sentiment analysis is nice, image analysis is nice, but that's not really too real to me. Let's see how it works in science. So then the project was joined by Wusuk, now back to KAIST University as assistant professor, and then Francois Lunesi, some of you might have heard, who have been working at Fred Aring, an astronomer, and his colleagues, Bohin and Liu from the Berkeley Cosmology Center. So here, what happens is that they already fit a ResNet for this particular problem with simulation data, so they know the truth. So there's something called omega m. It's one of the many parameters we think have something to do with the origin of the universe. And you can do this PDE forward simulation to get the purple image. That's what we could observe use this gravitational lens telescope. But we know we simulate it and we see which method would recover this omega m. So this omega m is kind of an average measure of mass in the beginning of the universe. They already did their model, right? So we came in because our method could do the interpretation for any model already trained. And we designed it from the machine learning problem, more from the input domain, the image. But then cosmology said that we care about the Fourier domain. We want you to interpret our model in the transform space in the Fourier domain. So we generalize a method. We have a method called trim to be able to now interpret things in this domain. So what you see is that you have an invertible Fourier transform T theta, and then you now, F is already a fitted deep learning model. You put that together, that's still known because it's a fixed transform, and you look at interpretation through this now, like a compositional F prime. And then if you use that from a CD in this transform space, then you can see that this around 0.25, this frequency band, you have the most important input to estimate omega m, and kind of made sense to them. And you see the high frequencies are not that important. And then I have been wanting to connect wavelets with deep learning for a long time. We followed the scattering transform of Stefan Mallet's group, but we didn't do anything until I said, now they're already going to Fourier space, let's go to the wavelet space. And independently, Francois and the cosmologists also want to go to wavelet space because they already actually have work by different people estimate this omega m in the wavelet space. But what I wanted to do is we have a data-driven wavelets, and what they did is fixed wavelets. So there's another paper in NERSC actually now 4 years ago, and usually when I do general methodology development, I want more like external validation, usually cross fields, right? This is a tradition now people try to capture in transfer learning, and it's a tradition in medicine called external studies, but that's remain medicine. We actually, as a statistician, I think our method should work across different domain areas. So we started with sentiment analysis, went to cosmology, and now the last author is my collaborator from the Berkeley Advanced Imaging Center, Bioimaging Center, Gauko Upayayula. We have a cellular biology problem. Chandon and Wusuk already working with him out. I think only Chandon and Xiaoli. So distillation actually started from Hinton, right? I mentioned Hinton, one of really pioneers of AI. Tia mentioned that I tend to go to cold field even without following the trend. Hinton big time, right? When the cold winter of AI, he continued to study, work on deep learning when everybody else was doing other things. So he pioneered also this distillation, because recognize the big deep learning models are very big, hard to penetrate. Therefore, maybe they try to make it into a smaller model. So now people call teacher model and student model in the AI literature. But people also try to interpret through additive models and decision trees. So this idea to make it into a simpler model is called distillation. What we want to do, I think we're the first to relate to wavelets from deep learning. People did do wavelets from data, do data-driven wavelets. We didn't know that, but there were people, apply math did that, but it was not connected to deep learning. So we're the first to connect the data-driven wavelets with deep learning. And you're kind of using this super amazing power of search to backpropagation deep learning to find a good place, and then you learn the knowledge from it. Because you have good simple wavelets, physical scientists love it. You have interpretability, compression, and efficiency all at once. It's this one slide tutorial on wavelets, right? Time series, basically you're cutting the time frequency domain vertically. And the Fourier transform is going the other way, right? Everybody's going to have the same wave form, regardless of time. Wavelet transform is being really saying that how the nature signals come about, right? We don't really care a lot of the high frequency signals, so you don't need to cut it so frequently. Maybe some problem you do, then you should do different timing of this time and frequency in space. And 20 some years ago, I worked on wavelet from compression point of view, from signal processing. So that's why I always thought this is one of the most beautiful mathematical objects, also reflect reality and engineering. So it's one of the things that which is really have multiple good properties. So that's why I wanted to return to wavelets. And also I work on neuroscience, and there's also a connection there, right? So and there are two great books by Mallet and Mayer. And beyond my interest in image compression many years ago, almost 30 years ago now, there's also, you see that this wavelets kind of come up from the first layer of AlexNet, right? It's basically try to mimic the V1 visual areas that even in supervised learning, the AlexNet was trained on ImageNet. But the beginning is really representation learning. And you see that using something called sparse coding, just use image patches. It's work my colleague here, Bruno Auhausen and David Field from Cornell. So how do we make a deep learning into data-driven wavelets? So this is a very busy slide, so I'll go slower. The idea of putting something like wavelet transform, think about the train we did. We did the Fourier transform, right? We called, I think, big T or something. Now we call it big psi. And if you know a fixed orthonormal wavelet transform, you can put it in the middle and call this new F. And the last part is the pre-trained deep neural network. Okay, so this is the first graph means. And we want to see how the deep learning attribute to the wavelet coefficients. And machine learning, a lot is designed a sensible loss function, right? One way to build in physics into deep learning is through this same thing. You add penalty terms that respect physics. That's a quick way to build physics. Or you can open it out, that's more sophisticated, to have the physics principle embedded in the structure or architecture of deep learning. That's more sophisticated. But easy ways have something, constraints, and put it as penalty to enforce physics that way. So what do we have are three terms. One is saying that I want my transform more or less reproducible, right? More or less invertible. You don't get exactly, but we want this transform per side not to be too compressive and not too expensive. And the last loss, you already saw that, right? I already did that with CD, which is now changed it to a simpler thing because CD is more computational to calculate. So we now use L1 penalty as interpretation loss. So I'm going to expand on the middle term. This is the term enforces wavelets, right? You could place this term with physics, right? Then you'll have a different thing, but we're doing, and the L and H are the low pass and high pass filters, which are equivalent representations of wavelets. So we're looking for this wavelet representation through filter banks and high frequency and low frequency. And we do stochastic gradient descent. So how do we do this? It's really Wusuk and Chandon who did it. I said, let's do it, and they did it. So I give them the books, right? And what they did is actually very effective and smart. It's turning all the equations that these wavelets, filter banks, need to satisfy, square them as penalty, very machine learning. So there's some condition like 7.31, it's really infinity. We didn't, so we just ignore that because we don't have to get exactly wavelet. We just need to get something like wavelets. And then we look at another book. If they overlap, this penalty approach doesn't matter too much, it doesn't have to be independent. You turn into another equation. Right, so that's how we got all these different terms. I also want the sparse wavelet coefficients, right? So that's the inside there. That's how we turned wavelets equations into constraints. And this one already mentioned, we didn't do the CD because it's more expensive to calculate. We used the L1 sparsity penalty. So back to the cosmology problem, how are we going to estimate omega m? This is also a very busy slide. Let's see that you see that purple image is what you can measure with gravitational lens telescope. And Francois and colleague already fit the ResNet through simulation data. And we use AWD, we call adaptive wavelet distillation, called data-driven wavelet. That's what I'll give you some examples. We did kind of a Cartesian kind of wavelet together. We didn't do the directional. And then there was already a method in cosmology called peak counting for fixed wavelets. So we just replace one step, this cosmology pipeline, with data-driven wavelets, okay? So you look at the lower part of the slide, you have many numbers. This is the mean square error, root mean square error. And there's this little multiply 10 to the minus 2. So all the numbers should be multiplied 10 to the minus 2, so I don't have to write all the zeros. Okay, so that's the precision. And then the first one, you want this to be small. And this is an estimation error for omega m. It's 1.0, something like that. And then you look at ResNet, it's 1.15. So we reduced the mean square error, root mean square error by something like 10 to 15%. Okay, so that's definitely a gain. And in terms of parameters, we reduced the parameter from 10 million to about 1,000. So it's like 10,000-fold reduction of parameters. We just went to the wavelets space and get the wavelet coefficient. So there are many other things in this table. Look at the last number. This is like without using the deep learning, just do data-driven wavelets, right? I'm referring, and then you get 1.3. So now that's good. Not as good as ResNet. And then the middle one just use fixed wavelets, and their Roberts cross is not too bad, but still 1.2, 1.3, worse than ResNet. So that's why they like the ResNet, because it beats all the other methods. They didn't have the last one because this is doing data-driven wavelet. If you look at the wavelets, we selected. So we actually the one use cross-validation. We got something quite symmetric. So this algorithm, if you start with something that is random, doesn't converge. So we start with any wavelets because you want some sparsity, something like wavelet, and then the algorithm converges stable, relatively stable to the reasonable starting points. And this is really trying to collect the mass, right? You apply this filter for different locations, you have 2 dimensions. Then you're really exaggerating, you're not just taking the mass, you're kind of exaggerating because the going down of the neighborhood, I have more like exaggerate the mass measure. But it's symmetric, right? Even we started, place is not very symmetric. So this is interpretable. Meaningful, that's what people think omega m is about. This is what this wavelet try to go after. I always want external validation of methodologies, not just for a particular problem we solve, because I see myself as a generalist, and I want the methodology to be applicable to other areas. So we happen to be also working on a cellular biology problem. And this is a problem with Gauko's lab. And Xiaoli and Chandon were engaged. We're still writing the paper, got delayed. So this is a process called CMI. It's a very, very central process in cellular biology. It's how the vascular trafficking, how the things get into a cell. So the line is cell membranes. I didn't know about this process until I started working with ABC, Berkeley Advanced Bioimaging Center. So what happened? This is something like you have all these different proteins, this green stuff, and then the cargoes outside the cellular, and you kind of almost like a magnet, hook them together through the membranes. And then these proteins will force the membranes to kind of curve and then fold, and you have another protein actin come and cut it off. And then you unpack it and you get the cargo, food, top, whatever in. This is actually the process that, remember in the beginning we have COVID, the variant was called Delta. Delta actually used a different mechanism called cell fusion. But Omicron, that's where things become super contagious, hijack this process. That's how Omicron gets into the cell. I lost track of all the other variants after Omicron. So this is, I think it's an explanation why Omicron is so contagious, because it's using the same thing with the normal channel uses to get food into the cell. So the problem Gauko wanted us to work on is called molecular partner problem. It's a central problem in cell biology because this CME process is so central. The biologists want to track when this process is complete. And you can track it much better with something called oxalin. But it's cheaper to measure something called plastron, the orange. And if you use deep learning directly to these very grainy microscopic images, it doesn't work. So we have to use understanding into microscopic device to turn it into a time series. And then we can use deep learning. So it's not like this is, you can call feature engineering, whatever, but this type of very grainy images, deep learning, we haven't find a good architecture to do things like that. So we fit the LSTM. In the beginning, we couldn't do that. We did a lot of manual understanding with fit the model until we got more data and we were able to do LSTM. So same thing, not quite same. And we distill the data-driven wavelet. And then we just use a linear model because we didn't have this peak counting method and to do the prediction of the green time series from the orange time series. This way, the LSTM had about 1,000 parameters. And after the wavelet distillation, we did data-driven AWD distillation, we end up with 30. We took 5 scales, the 6 largest, to 30 coefficients. And this is our score because you want to be large. And LSTM is 0.23, and we can do the 0.26, so about 10 to 15% again. And it's interesting that for this problem, if we use AWD without using the LSTM, you get something quite close to LSTM. So basically saying that LSTM is not quite needed, but if you combine LSTM with our methodology, you do better than both. And the WC5 wavelet do like 0.2. So this is also like 30-fold reduction. And when you have 30 parameters, things is a lot more interpretable. And if you look at it, what you see is that now it's not a symmetric wavelet we chose. It's really try to see if the orange signal, the clustering, has a huge jump. We kind of figured out, right? Remember in the beginning, we couldn't do deep learning because we didn't have enough data. So we manually look at a lot of data and we manually put in a feature to capture the jump. So when there's a huge jump in the clustering signal, the orange signal, then it's more likely the process will be complete. It won't be aborted. So this is really agree with the human knowledge through our own data inspection. So what's going on right now? This has been going on a couple of projects. We're just writing the paper. It's a new project with 2 climate scientists. One is Da Yang, who used to be at UC Davis, now at University of Chicago, and Padram Hassanzada used to be at Rice, now at University of Chicago, and really led by Lin Yao, whose student died, and my student James Duncan, who is graduating and joining AI at the Institute for AI2. They have a climate science group, and also Asash, who's now professor at UC Santa Cruz. So we study MJO. MJO is an intraseasonal weather system for which Dai is an expert. Padram is more like an applied mathematician. And it's a year-round intraseasonal periodic pattern of rainfall that lasts 30 to 60 days. And what you see there is, it's kind of funny coloring. What you see is the moving of the rainfall. And when it's relative to the average, the red is actually less rain and the blue is more rain. I would have coded it differently, but I borrowed this. And then you have something like little circle, it's really giving the phase information about the location. There's something called RMM. So of course, MJO has direct impact in the tropics, but also have indirect impacts in the extratropics, right? Even in California, you can see that California, the atmosphere's river is impacted by this MJO. And my collaborator, Da Yang, published a paper in Nature, Climate Change, really emphasizing that MJO impacts where I am, not you guys. And there's also recent work by Chad Small, who really have this beautiful illustration seeing what's going on, right? It's a lot of convection and things fall down in a different place. And his emphasis is about catastrophic flooding in California, not just rain, but small coming from the like extreme weather point of view. He's looking at more extreme impact, not just prediction and sometimes less harmful impact. There are two dimensional index called real-time multivariate RML that's traditionally used in the MJO field. It gives the strength, it's like dimensionality reduction, strength and position of the MJO. And here just illustrating on March 5th, 2023, and you can see that the blue gives you the strength, and then the quadrants give you the named different parts is in Western Pacific. So what we try to do is we want to do prediction, but we also want to interpret good prediction models for understanding of the dynamics. So our model have 19 input variables, and the RMM actually is built on 3 of among the same 19 input variables. But all these variables, you can see a lot is about pressure, so they're related. And there's also very important ORL, outgoing long wave radiation. You have water vapor, total precipitation, temperature. So this is the variables we use in the prediction model, but we're really predicting RMM, which is dimensional reduction, which have been used scientifically to understand its strength and also the location. So the hypothesis we came in with, because Dayang's work, is MJO large scale phenomenon or small scale phenomenon? Is that moisture mode or gravity wave? My guess is that actually it's probably both, but the question is how much both. Mostly probably going after the large scale. And local scale probably will be interesting for the next step. So we built a UNet. UNet have been used in climate science and take the architecture, we trained on our data, and we have a small dense MLP to take things out from UNet. I'll show you in the next graph. And the European model is a numerical model through numerical simulations, can do 30 days, right? They also use, there's another one called ROM, it's related, but we're showing both. We use RMM mostly. And the US model only can produce 19 days for the RMM, but I'm also showing you, if you look at ROM, you can do further. UNet, we actually beat the US model and a lot cheaper by 3 days. And this is the UNet, about 34, 35 million parameters. And we also have a small, relatively small, like convolutional network model. We have to put it together, but the architecture is mostly taken from this work, Ronenberg. So now we want to use interpretability, right? Actually, I engage in the project just believing AW will be useful. It's my very, like Tian was saying, taking risks. I just have a belief that wavelets is important, physical science like wavelets, so it's going to be useful. I mean, all the things, the details, we're working in that out now. Just because also wavelet is mathematics very elegant. So different reasons. So we said, let's just do this. And of course, my very talented collaborators and students really carry this through. And I have been very engaged in this project, meeting like bi-weekly. So here we don't have as clean picture as the cosmology and cellular biology problem. So we have to extend AW because AW originally was developed for one single scalar response. And here we have 2 responses, so some computation problem James had to solve. And we were able to use AWD to clean the input more. Like people already use Fourier space to do deep learning. So this we use data-driven wavelets in the space and feedback to exactly the UNet. And we don't even update the weights. And then we actually increase the prediction horizon by 1 day. Even 1 day is not easy in this game. Okay, so we clean the data using a data-driven wavelets, but we're still using the same, 30 million parameter UNet. Or you give up a bit on prediction accuracy and use a small, much smaller CNN after the wavelet decomposition and then we lose 1 day. So unlike the first two examples, we gain both predictability and interpretability. Here, there's a trade-off. It could be that we're not working hard enough. We're doing something still, not giving up. But right now, we either get 1 day gain by using adaptive wavelets, or we lose 1 day, but we have the interpretability. And we really see that the ones chosen are really large scale kind of wavelets and really backing up the large scale theory. So back to my schematic plot is that for the first two case studies, I was able to do both. My interpretation of this is that for those problems, the signal is very clear. Wavelets just give a very good basis to explain the phenomenon. For the climate model, things are more complex. We don't have all the input variables. There are a lot of impacts. We're only looking at also, I think, 15 degrees above and below the equator. So we don't have, there's a lot of impact from other parts of the world. I said, the impact to California. So we don't have a clean signal. And therefore, that's why I think partly explains why we cannot achieve both. But we have really good match that wavelet is the right representation and data-driven so that adapt to your problem, then you gain both. So I want to go to the second part of vertical data science, right? And if the process is not trustworthy, I don't think you're really shortcutting yourself for get the best results. So this paper I mentioned earlier with my former student, Kumbir, who's at UCSF, also doing a startup with a neuroscientist after a postdoc. This is a framework trying to realize the promise and mitigate the dangers of AI. I started with AI. Here, the dangers of AI in science is really about we have too many false discoveries, right? There's no direct harm, but the harm can be really everlasting. So it's like, can we have control the false discovery in science? And thanks to Tian again for suggesting this great name for our work. So the framework is measuring machine learning and statistics, takes predictability from machine learning and statistics and computability, and also hugely expand the uncertainty concept in statistics from sample to sample to the whole data science life cycle, and also take advantage, like integrate, not like provide a big tent, talk about numerical stability from control series, so become perturbation. You justify in your documentation why there's a reason perturbation. And stability is really a common sense principle. It's an Asian philosophy. Plato in Meno said that opinions change, but knowledge has to be tied down. And that means it's stable. And climate science, you guys already leading, that's what I cited, right? You have 9 models from IPCC report. I was doing TCS uncertainty quantification without, because we developed later, that was really one thing that inspired me to get this right, because scientists are already doing it. And so we did stability analysis. We have 5 random initializations, and to make sure that we have the same for this cellular biology problem, kind of the same wavelets. And then we also use only 80% of data, you get stable results. So we did some stability analysis. The predictability already done, so PCS and the computation is always there. And same thing we also did. So basically we checked stability. So where we're going is actually finishing the project with MGO, and also starting, just finish a proposal with the Mathematical Foundation for AI with a bunch of people, especially with Pedram from Chicago, to really study turbulence. And there is challenge because we have high dimensional response for turbulence, and we need to really speed up AWD. We put in a bunch of ideas. So the code is available, so especially you have a scalar response. So before I give more information on the side, so if you guys are doing fine tuning of a climate models, we have 2 very related, very different work using both some mathematical work called MuP, developed by Greg Young and colleagues from my Nikhil is now postdoc at the machine learning group in Flatiron, and Sophie Hayu is on the job market. He's fantastic, both of them fantastic, but he's on the job market if you got interested. So here we show that if you do fine tuning, you don't do full model fine tuning. when you have uses low rank two matrices, people usually have the same learning rate or step size. You should actually use different step size. And we have some recommendations based on some math and extensive simulations. And we have another work which just got into NERSC. The other one was the ICML this year, to show that when you initialize this A and B, they're not equivalent either. People usually set 1 to 0 and the other one to IID Gaussian. So you should set B to 0 and A to random. So check it out. And I want to end with the book which just came out called Vertical Data Science by MIT Press. The free version came out actually in February, and I think Tian got a copy, sent me a photo. I also have my copy now. So check it out. You can use a free version, of course. And its intended audience is domain scientists too. It's not for courses, goes really well with a more mathematics driven. Like we try to not have too much overlap. It's more about the ideas, critical thinking, and the whole data science pipeline, data cleaning, GitHub, collaborative research. So try to fill the gaps and mirrors the data science lifecycle. Emphasize problem formulation, data preparation, and it's comprehensive and coaches critical thinking. And PCS is an overlay, and the code and data all available. And we move away from the traditional board, there's a true model. We think about as a practitioner. Usually, you guys probably have more sense about true model. A lot of time you don't have the true model, and you write documentation with fine kinds of exercises. There's some software available to support you to PCS. Both, and we also wrote a paper now being revised for simulation guidelines, how to use data. And the SimShelf is the R package, help you do multiple simulations. It's kind of using stability principle in the simulation world. In the theoretical world, I think we should do multiple stylized theoretical model to analyze a particular useful empirical method. So PCS has multiple roles. You can do new algorithms. You can solve frontier scientific problems in genomics, clinical trials, and clinical decisions, and have been extended by others. Like Tian has written papers on network analysis, and Murphy to reinforcement learning, and Peter Cauldron from UCST have extended spatial statistics, and we are working on uncertainty quantification. My group, chapter 13 of the book has something already. We're just doing more data results on that. Actually works. And it's really a philosophical and conceptual practical framework, documentation, and you need to use domain knowledge to reason why something is a reason perturbation. And I'm hoping to do some program at Siemens to build theoretical foundations on stability. So a lot of the approach I take, it's really very much in context approach. This is actually by Ward, was founding members of the Columbia Statistics Department. I gave a Ward lecture, so I was digging into the history 2023, and there's this great description about in context approach. I make the name in context. You start with a practical problem, you get a true feeling for before you do extraction of mathematical extraction. And I think this is just some musings about how we can work together. It's more for the students that we meet in the middle with mutual respect and take concrete steps and really argument each other's strengths. And we hope we have a funding promotion structure I think the center has to facilitate the collaboration. And to reflect my own experience as a generalist, you really have to take opportunities. And your other value system definitely impact me. I think in general, very curious person. And I take risk, I would say more calculated risk. And then societal importance is very important for me. And you need to find the right match of people, communication skills and personality and values, and to work, find collaborators, and be willing to dive into a very new area. And there are many ways to do that. And I want to advertise for Siemens Institute for the theory computing at Berkeley, that we have put up so many good workshops. This year is large language models. So just to search Siemens Institute, you'll find all the workshops listed there. Just really wonderful program. You can also come or just watch online. So the two programs, large language models, will continue to the spring. And then there's new paradigms in generalization, more machine learning program. So the papers are here, and thank you very much. I think I went a little longer. Yeah. Questions?
Yeah, we have some time for questions. So, Mom says she's gonna pass on the mic. Yeah, there. Or you can just speak loud. I think that this thing works.
Hello, can you hear me? Yes.
Yes, I can hear.
Professor Yu, thank you so much for this great talk. That's very interesting. So one question I had is you like a very common concept or buzzword, let's say in ML, is explainable AI. And I found it interesting that you haven't like brought it up in some way. There's another, like Cynthia Rudin is a professor, I think, from Duke University. She's a strong, she's opposed to this and brings also forward this concept of interpretable AI, right? As opposed to the explainable AI. I just wanted to know where you position your interpretability.
I don't think, for me, I think the terminology have evolved, right? So for me, interpretability and explainability are pretty much the same. I know people are now differentiating it, and I don't have the latest on this terminology involvement.
I think where Cynthia stands is if you have a choice between using a black box and then apply explanation method afterwards, like using Shapley or something, versus using an interpretable model, that the model itself is more interpretable and more transparent, then her advice is do the latter for high stake application.
I follow her work. I have another talk we reference her on decision tree. She has been working a lot on decision trees, and I just not on top of this evolution of the terminology. Thanks for argument that. So I kind of still use them more exchangeably, but I might have to conform at some point. I emphasize the audience. I'm more really in context, working with scientists, and then hopefully it will be general. I think the terminology have evolved. I haven't caught up with the most finest interpretation of the terminology, but I kind of put them together still in not making the distinction.
Yeah, so if I understand you correctly, for you the relevance and the insight is basically at the core.
Yeah.
Okay.
Yeah. I should probably update my terminology, but I haven't. Yeah.
Okay.
For me, it's solving the problem and who benefited.
Yes, thanks a lot.
Yeah, thanks for the question. I need to ask my student to update me on these new terminologies. Yeah. Yeah, I'm very pragmatic. I want to see things really, there's ground, like impacts made on the ground and who benefit from it, what scientific knowledge we gained. But I should probably update my terminology usage. Yeah, thank you.
I think one thing I want to make a comment on asking for your insight. Yesterday, in a very unrelated discussion, we realized that research, sometimes when you do collaboration, and then with different people from different field, we realize the formalism, the research formalism differ between field. What you presented today, even though when you present, you talk a lot about tools like wavelets, you talk, what is unspoken is the process, the guiding principles that are intertwined with what you introduced. And that is a formalism in statistics, in data science, that sometimes is hard to transcend to another discipline when uses different formalism. So maybe I just wondering, like, maybe is this something that you would like to introduce in your PCS framework, is to introduce the process rather than individual tools?
That's a great question. So there I have to collaborate with the domain scientists. So I did write a paper with younger colleague in computation precision medicine. Him and Ala at Berkeley, we wrote a paper called Vertical Data Science for Medical Foundation Model. So there he's more deeper into medical AI than me. So I collaborate with him and wrote a 4-page paper just to kind of lay out certain concerns we have using this framework. And I was talking to some biologists in crime EM in at Fred Irving. I was there a couple of weeks ago. And talking to the postdoc and his advisor, hopefully we can maybe write something, kind of unpack the principles for crime EM and match with their process. And my conversation with people like Shirley Ho from astronomy, she thinks that they're already doing PCI stuff because they are pretty rigorous. So there probably they just have their own names, but there was a national like NSF AI, we put in a proposal, didn't get it, but the astronomy in Berkeley would seem to be very open, like to have something into. So you have to work with domain scientists. And we're writing a paper with sociologists, with my student Zach, right now in Munich. They, because did what you probably heard from Andrew Gellman, the multiverse, and we try to merge the two frameworks in social science problems. So you really have to collaborate with other people who know more about the domain and either try to integrate. And yesterday we had a really great Neyman seminar by a philosopher called Deborah Mayo, who has written a paper, tried to do the history for statistics, and she proposed a philosophical concept for severity testing. It's basically saying you want to make sure all the errors, as much as you can, have been ruled out from the process, but very high level. She's a philosopher. So we're talking about how do we bring the two framework, at least have a discussion about that in her blog or something. So really collaboration is the way to go. And you need to build trust, and people need to really feel it's worth it to do this. With cancer detection, I have been working with different people at MD Anderson and also Michigan for the last 5 years, through introduction by Hutchinson people. There, they invite us to do a software proposal, which we did with my former student Tiffany Tan at Notre Dame and Kenny at UC Irvine. We put in a proposal to put this idea into a cancer detection software. So that's really getting to their process. So it's really different, taking opportunities and work, be patient. I think it's a very long answer to your question. I don't know if I answered it.
We have one more question on Zoom, and then we're coming up on 1 o'clock, so we'll need to wrap up. But from Sambit on Zoom, thank you, Ben, for a great presentation. Could you please expand a bit on the application of AWD approach to turbulence, parameterization, emulation, especially in the context of atmospheric LES models?
Yeah, we are doing it very simple 2D turbulence. And we are using something called subgrid. Basically, you do a numerical simulation at the Cursor scale, and then you have this residual thing, and people feed CNN. We try to interpret that. And for the emulation, you can also put that back for emulation. So it's basically looking at the subgrid stuff. I hope I answered that. But it's very simple. Very simple turbulence now. Hopefully we'll have something. We just put in the proposal. We have some initial result which look promising, but there's substantial computation problem we need to solve.
Okay, thank you, Ben, so much for such a wonderful talk.
Thank you for having me. Sorry I couldn't make it in person. Yeah.